Hi there, my name is Valery Kravchuk and I'm recording this session for MinervaDB database conference from our family house somewhere to the north of the capital of Ukraine. This talk is devoted to dynamic tracing on Linux and its use for solving all kinds of performance problems. At the moment and for last almost 5 years, I am working as a principal support engineer in MariaDB Corporation. But the approaches and problems discussed during this session equally apply to MySQL, that is like a main topic of it, MariaDB, and more or less any process that you would like to study and solve performance problems for on any modern Linux version. Previously, I worked for Percona, Oracle Sun, MySQL, so I'm more or less in this business for last 15 years and a half. Since I quit from Oracle, I started to speak and present about MySQL and related technologies in public. I've created my blog that initially was devoted to bugs. Historically, I worked in bugs verification team in MySQL, so it was natural for me, and still is, to think about MySQL in terms of bugs. I also created a Facebook page, a Twitter account called MySQL Bugs, but with years, and specifically since I joined MariaDB, I am not only writing about bugs or MySQL bugs, but also try to present solutions to some common or typical customer problems I hit in my normal work. So in the blog post and elsewhere, you now can find a lot of stuff, not only related to bugs, but still it was mostly my bugs related public activity that made people think I'm good enough to be declared the MySQL Community Contributor of the Year 2019 last year at Percona Live conference. You can find my different talks here and there. To summarize what I do, at work I like to solve problems, and as I'm in this business for more than 15 years, I think that I know a lot of things and a lot of people who are responsible for creating and solving problems in MySQL community. Even though I work for MariaDB Corporation, my participation in this conference is solely my own idea, and I speak only for myself. This is the case since I quit Oracle, so it's a kind of a standard disclaimer. The corporation views and the views of any of my previous employers may be quite different from what I express here. I try to be honest and speak to the best of my knowledge always. So this session is about resolving performance problems. To resolve performance problems, you need to collect some data. You have to find out where the time is spent, what's going on, and in case of MariaDB or MySQL, there are different sources of such information. First of all, historically, developers, for example, when they solve problems, they often work with debug binaries, and debug binaries that are built in a special way allows you to use so-called debug package that in turn allows to dynamically enable tracing at the beginning and at the end of most of the functions on the fly. So as long as you have debug binaries, you have quite a interesting and useful way to enable different things and check what's going on, even without detailed study in a debugger. For normal DBAs, there are also a lot of tools. First of all, there is a slow query log that you can make logging all the queries. Mostly the task of the database system is to execute queries. So as long as you know which queries are executed, how much time it takes, and in extended slow query log, how the query was executed, had the optimizer decided to use temporary tables and so on. So with all this stuff, you have quite a lot of tracing and even profiling insights inside the query execution. That is the main task. By the way, historically, before joining MySQL, I was a trainer, and I've got this habit of creating slides which are like a table of content for whatever I'm going to speak about. So whenever you see on my slides anything highlighted, you can just click on the link and get more details, being it my blog or MySQL manual or whatever. So the slides themselves, which should be available by this time to you, and this information should be shared on Slack for MariaDB conference and elsewhere in my social media. So they're available and they can be used for further reference. So let me continue. One of the initial sources of profiling information in sense of counting how many operations of each specific kind were executed was show status SQL statement. In case of InnoDB, you can get a lot of insights by checking the show engine InnoDB status. Historically, people used to study show engine InnoDB mutex output as well when checking where waits are happening, why nothing happens but still CPU is used. Later, a lot of InnoDB tables related to logs, for example, log waits and similar stuff were added to the information schema that appeared in MySQL 5.0. Even more later, thanks to Percona, the so-called user stat edition became popular among MySQL DBAs. It's used by default in Percona. It's available in MariaDB as well, not in stock MySQL though. So you can see how many operations are executed per user, per specific client connection, per table, or per index. So it was a great source of information to find out what indexes are not used or which are mostly used and so on. Another interesting stuff that appeared in 5.0, somewhere after it became GA, was the first community contribution by Jeremy Cole, show profiles. It's specifically about profiling. So basically, the execution of SQL statements were split into several stages, and for each stage, the time spent on this stage was counted. So there were quite detailed splitting of the time. And by enabling profiling and by using show profiles, you can see not only why the statement was slow, but at what specific stage it was slow. For all these methods, the common feature is that they are not detailed enough, and it's not even enough to check stages, because each specific stage, like sending data, for example, those are from show process list, by the way. So this stage may involve a lot of operations, and some of this operation may involve waits. So based on the idea that more details are needed, and the problem that profiling and tracing should be lightweight, not like enabling the debug prints, but something much lighter and much less affecting the production use, the performance schema was created. The performance schema appeared in MySQL 5.5. And until these days, the main source of profiling information in current MySQL versions and friends. So the idea was that information is collected in ring memory buffers. So with fixed amount of memory, you are able to collect recent events, including timing if you asked about it. And when you are interested in finding out where the time is spent, you execute SQL queries against a quite complicated with dozens of table schema called performance schema. So the aggregation may take a lot of time, but it happens only when you ask about it. The data collection itself is quite lightweight. Ring memory buffers is a great idea that's used in many other places as well. So besides that, surely as we speak about the open source software like MySQL, we can see the source code, we can have symbolic information in our binaries, and this makes the use of real class of software programs called profilers possible and reasonable. Being it a simple profiler based on actually a debugger like PTPMP, poor man's profiler created by Domas Mituzas, and later a bit advanced version of it is included in Percona toolkit under the name of PTPMP, or real profilers of those By now, the most important one that remained in use in Linux is Perf. So basically, we are moving to the next stage. So we can apply operating system level tracing and profiling tools like Perf or GDB to any process, and MySQL or MariaDB server is just one of the examples, so why not? The last but not the least, you can actually, if we speak about clients that connecting remotely to the server and sending queries, they are sending their queries and getting results over the network. So yet another approach to get profiling information and queries and time spent and the amount of data passed here and there is to study the network traffic actually. And we come to the TCP dump analysis that is also widely used. Of all this, for this talk, I picked up specifically this approach. Operating system, in our case, Linux tracing and profiling tools. That's what I'm going to concentrate on. That's it. Speaking about Linux, there are three main classes of tools that I would like to discuss. The common idea behind them, there are two common ideas. We need tracing and profiling that is as lightweight as possible. And ideally, we would like to use the same approach to tracing both to MySQL server and to the rest of the operating system kernel, disk I/O routines, scheduling, whatever. So it must be lightweight and it must be system-wide. That's the ideas behind using the tools. Three main tools are, first of all, it's so-called function trace or ftrace that was introduced like 11 years ago in Red Hat Enterprise Linux 6. It was already available at the early stage. Another step that happened quite soon after introducing ftrace was the addition of so-called performance events and implementing Perf profiler on top of it. And Perf profiler is a convenient way for adding what is the main topic of this talk, so-called dynamic probes. That is adding tracing and profiling events on the fly to already existing code without changing the code itself. That is cool. And recently, starting from Linux kernel 4, and especially in Linux kernel 5, with whatever Miner version, another approach that is even more lightweight and more powerful called extended BPF, where BPF stands for Berkeley Packet Filter, initially a thing used by TCP dump that I mentioned. So the eBPF approach and the ways to use it via BCC tools and compilers or via recent front end called bpftrace will be like a final and most future-proof and interesting long-term solution to the dynamic tracing problem. I base my presentation on practical examples of my own, mostly, and somebody else's, of the best of colleagues in the community, users of these dynamic tracing approaches to solve the performance problems, and in the process we surely hit the problems of the dynamic tracing approach itself. So I discuss them as well. The main idea, let me highlight it again, is the performance impact of tracing and profiling that we apply. You may ask why I do not speak about the performance schema specifically. First of all, there are too many talks about performance schema already made, including those by myself this year. So there is not so much point. Now to more practical problems. What made me rarely use performance schema for last 4 or 5 years? As I work for MariaDB, most of my customers do use MariaDB server. The MariaDB server, for example, the performance schema is not enabled by default. There are builds like Facebook MySQL where the performance schema is not even included. It cannot be enabled. It's removed at compile time for the performance impact that may be visible, which is more interesting and applies to MySQL main MySQL as well, is that the instrument you may need for your specific performance problem may not be enabled at startup. And unfortunately, as I had shown in, now it's my obsession with bugs, in my old bug report that is still not fixed, there are instruments that cannot be enabled after start of the server, so you would have to restart it. Moreover, some of these instruments are not actually documented as such, so you do not know until you try and you fail. So your statement to enable the instrument works, but you do not have it enabled. That's unfortunate. Performance schema is based on the idea of memory buffers. So they are ring memory buffers, and if you would like to study performance for a longer period of time, you have to use large buffers. You have to set their size explicitly because default size might not work well. So sizing of instruments in practice was quite hard, as I found out hard way 4 years ago. And it's an iterative process that may still do not give you the outcomes you think about. You always can find out if you missed some events. This is reported. But what is the right size and how to find the trade-off in between additional memory allocated for this stuff and the results you collect there, it's not obvious and not clear. As I work mostly with MariaDB, I have to work with many additional, often third-party storage engines and all kinds of plugins, for example, Galera, that may not be instrumented at all or in enough details. So one of the examples, again, was reported. This, by the way, does not apply even, it does apply to Galera, but some stages of statement execution in MySQL itself are also not properly instrumented to enough details in performance schema to solve practical problems. What's most important in current context for me, that performance schema, even though it's improving with each version and it's quite detailed and great source of information in MySQL 8.0, for example, does not provide me with a system-wide profiling. So I don't know what at the same time happens at the operating system or file system level. I have to use two kinds of tools, performance schema in MySQL and something else elsewhere. So why to do it? Why not to use this something else for MySQL server itself? Another minor thing, quite minor, but still important for me, is that in MariaDB, historically, performance schema not only disabled, but it's for a reason. The developers, when they work on performance problems, they always prefer to get profiling information, backtraces from GDB and whatever, but not just partial information that is provided by the performance schema. For me personally, writing complex enough queries for practical problems to performance schema is also not easy, so because they may be many pages large to get the details I need, but here C schema that is for quite some time a part of MySQL often helps. So let's say it's my personal problem that I do not like to write really huge SQL and do not have a set of ready-to-use scripts to just share. Too much typing, I don't like it when it's not really needed. So what do I suggest instead? Instead, I suggest to use the tools that are available in Linux itself, and were actually added by Linux kernel developers to profile, trace, and study the kernel itself. The kernel is a more low-level and more often used and more important part of the entire setup than even MySQL server. So if the approach works for functions in the kernel that are called way more often, and if the resulting performance impact is acceptable for Linux kernel developers, then they should be acceptable for all of us as well. So yes, I am going to speak about user probes, trace points, all implementations of dynamic tracing we have over the last 11 years. And if you are interested in a lot of details about this approach and how to implement it, I refer you to mostly to the site of Brandon Gregg, who is working for Netflix, to his book, recent one that appeared this year, that provides a lot of details on everything we can see on this diagram of various Linux performance observability tools. Of them, let me remind you, I am interested in Perf, ftrace, BCC tools, and bpftrace that allow to study the entire system, so they are system-wide. That's a key. And they are modern. There were tools in the past, like SystemTab, for example. But there is no point to use them these days because what we have now is way more powerful and at the same time lightweight. So when we speak about tracing, we speak about doing something, basically printing something, saving some information whenever a specific event occurs. What events we are interested in? I would like to split them into two categories. So the events that can be added and happened, like kind of happened automatically, so-called automatic events, versus the events that require some work from the developers of the source code of that specific component. I would call them manual annotations. So if you have to change the code, like it happens with performance schema in MySQL, you have to put specific code for some stage to be, or for something to be traced in performance schema. So I would put it into the category of manual annotations. So another dimension is it in case of Linux in the Linux kernel, drivers or whatever, or it's in a normal user space. So from this regard, we have automatic in-kernel kernel probes, automatic that is absolutely dynamically added in the user space, user probes, specific code added to the kernel to help tracing its kernel trace points, but when it happens in the user code, it's called userland statically defined tracing. Or basically, for historical reasons, it's called dtrace probe because it was dtrace initially in Solaris that added this feature to add trace point and then use it in dtrace. Linux inherited the syntax of trace points, so that even though the dtrace itself was not available until recently when Oracle decided to use it, it's available in Oracle Linux. The syntax was still used by the similar tools so that they can continue to work. For me specifically, the most interesting part here is user probe or uprobe, a way to trace user space function calls and more. So how to work with these event sources? You have to define the event source somehow. As we speak about Linux and Unix, it's natural to expect that defining something and working with something is involving creating and writing something to text files and maybe reading something from another text files. This is how ftrace is operating. And this is how all that was added initially. So all you basically need if you would like to work with event sources by hand is that you need to know the naming scheme. You need to be able to create and work with text files with basic tools like echo and cat. So this works via a special file system that we will discuss later. Usually it's a part of a prods or C's file hierarchy. And when you create and enable some event source, kernels start to work somewhat differently. But basically, dynamic tracing as a key point of all this, it means literally this. The code of the code that is executed, kernel code or user code, is modified on the fly. The idea is basically not that complex. There was a GNU profiler, and GNU profiler was working by adding specific code to the beginning and end of each function. So this mechanism already exists and was then used by kernel developers that made it possible to add some tricks so that this code is changed from no operation to call to specific part of the code that you define. So if you're interested, you can find out how it works. But basically, you do not work, usually you, especially the DBA, MySQL DBA, do not work with these low-level tools. And you do not have to as soon as you are able to install some front-end packages and if you use modern enough Linux. So you use with this underlying mechanism via front ends. And from this point of view, Perf profiler is a front end, BCC tools are front ends, and bpftrace is a front end. So they simplify the use of all this stuff. But when front ends are used, actually still the files are created, some text is put there, you read from the files, you can just do it in kernel context and not necessary from userland, echo, and cut comments. So ftrace. Ftrace in modern Linux is based on the special file system, syskernel debug tracing that you just have to mount, and then you can see a lot of content there. If there are some tracing events, for example, user probes, you will see them in specific files. For example, here we have a user probe for MariaDB 10.3 server. You can study all this in details by following the links, or we can consider an example. What's good with ftrace? It's readily available on any modern Linux kernel 2.6 to 2.27. That means everywhere. You do not need to install anything, no compilers, no profilers, nothing. Basic steps are like that. To add the probe, you need to find out the address. That's the most complex part. So to which specific address in the code you would like to add your probe. One of the easy ways here, it's presented based on the example of MariaDB 10.5. So you can apply objdump, for example, and search for specific function name if we speak about adding the probe to specific function. And you will see the address. So ftrace works with addresses. So if you know the code of this function, you can find out what are the arguments, you can do something with them. If you know how arguments are passed on your specific processor, then you can even print them or use them. So basically, this is how it works. We have the address. We are adding a probe, P. We give it a name, DC. If you do not give a name, it's named automatically. For dispatch command, it's one of the MySQL functions. This is the binary. MariaDB, it's the executable of the server. This is the address. And here I say that I would like to give a name query to the third argument. I know that it's passed via the register. This is how to refer to it without the offset. So just like hieroglyphs, for now you can accept it that way, but there is a logic behind that. And I would like to print this argument as a string. And this is a probe that you add to user probes. You can append to user probes. Here I'm adding one user probe. Then after adding all your probes, you then enable them. Whenever you add the probe, there are new files created. So you see a file, a directory created under the uprobes named after the probe itself. And there is a file enable. If you put one there, the probe is enabled. Then you enable tracing itself. For all of the probes, you put one into another file tracing on, and then you read the tracing information from another file, tracing trace pipe. There are many of them. So different sources with different options, hierarchical output, whatever. It's a huge topic for many hours of tutorial, by the way. So what you see as a result, you have a binary name, process ID, you see where this specific function was executed on which CPU, on 0, CPU 1, on different cores. Time from the start of tracing in, what are these? Microseconds, probe name, probe address, and the arguments. So in this case, and through most of this presentation, my goal is to capture the queries on the fly. So the third argument is the query that is passed to MariaDB in this specific function. So I see that the query, that's why the name, was this one, select 1 plus 3. And all other queries are also traced. When I stop tracing by putting 0 to these events, I will not see any additional events here. There are more details in my blog posts and in tools created by Brendan Gregg based on ftrace itself. So the tools are actually shell scripts or whatever. It's only about reading and writing characters to specific files in the file system, nothing more. What about the problems? The common problems to all dynamic tracing tool on Linux, and I highlight it every time during the presentation, is that to use dynamic tracing, you need root access. It may be a problem at initial stage. DBA may not be given a root access, but if you are working with containers, for example, you probably have root there. And if you are just a DBA, you can discuss with your system administrators which commands you need and get sudo access only to them and explain why. To summarize, in my experience, over few attempts and showing how it works and what we might get, even huge banks with all their security of my customers are already giving DBAs these tools. They install Perf debugger, they install GDB, or Perf profiler, sorry, they install GDB and they give them root access to enabling dynamic tracing. It's beneficial. And it can be limited by sudo if they care that much. So another thing, you surely should know the code. You need to know what arguments are passed. If they are complex structures, you need to know how to deal with it. Besides the probe at the beginning of the function, in some cases it's really important to add the probe at the end of the function, at return, so what it returns. It's easy actually, even though it's a problem, you just need to know the syntax. The syntax is simple. You put R return instead of P for the probe, and you have access to such a meta variable called retval, so it's return value of the function. So similar to debug binaries with that tracing utilities, you have an easy way to add the probe at the end of the function as well and check what is returned, or how much memory is allocated, which file was opened, and so on. Theoretically, you should care to remove the probe when you are done. You can just minus it from the uprobe events if it was just appended, so the rest of the probe remains. So there is some procedure to follow, but basically you can work with ftrace. In practice, when you do not know what to do with ftrace, you can use a higher level tool that is based on ftrace, for example, Perf, and check what probes were actually created, and then you can do it manually. That's what I did actually. That's how I found out many of the details presented in blog posts. ftrace is still interesting, even though it's less practical than more advanced tools, so I keep studying it. There is a lot of reading here, and it's actually a link to the kernel orgs, kernel documentation of Linux itself. It's very interesting stuff. Soon after ftrace, and again 11 years ago, the Perf profiler was added based on ftrace and additional performance events added. Basically, Perf is a command line utility. It's a profiler that has a multitude of commands, and you can get help by just calling Perf, basically like this. Let me show. You can do just this, be enlightened on all the commands. So most important command that we are interested in is MySQL DBAs for solving MySQL performance problems would be perf record to record performance data, perf report to process them, perf script to output the raw data for further processing, perf probe to add in dynamic probes, that's my topic, and maybe perf top to see what it's like top utility itself, to see where the time is spent right now in specific process or in the system at all. So it's like interactive tool to get some insight of what's going on. So these are basic commands. Speaking about the adding dynamic probes with Perf, I again use the example of MariaDB 10.5, 10.5.6, just because it was one of the recent cases. So I'm interested in still in checking the same information I was checking previously, getting the text of the SQL statement executed. For this, I will add a probe to the same binary, to the dispatch command, and here I do not need to know which argument is it, how is it passed via registers. I can use names. So Perf is a symbolic profiler. It has access to symbolic information in the binaries if it's present. So I'm saying basically the same as ftrace, but there is a name for this argument. It's called packet, and I would like to print it as string. So then I collect the information for some time, perf record. It's stored by default in the perf data in the current directory. And this file can be quite large. So I'm collecting the information for all CPUs with some details. Then I can process this information, for example, with perf script, put the results into queries, and by the way, this is the probe that was added. It's exactly the same as I added manually. It was added by perf. And when I'm done, I can delete the probe as well. So it's basically the equivalent of previous test with ftrace. Now, what we can see in the queries, the information is actually also similar, just a different name to the parameter is given. It's like automatic packet, the name and string is format is added to the name, and I still see the same information. My point is perf uses ftrace as a background, basically, for most of the tasks. Just was created when more specifically profiling events were added to ftrace. You can control output format, but again, here you see the binary, process ID, which CPU it worked on, timestamp in milliseconds since start of the recording, probe name. It's more advanced, so by default, when the name is not given, it includes the binary name, the function name, there is address, and all the arguments. Perf is surely easier to use for dynamic tracing than ftrace, but you have to install it. It's a separate package. You have to add it. And while we do not need to care about addresses, we still need to know how the code is organized. So we are lucky that we work with open source software in case of MySQL, and we can just check and read the code, or trace it in the debugger and find out if we miss something. Problems. It's easier than perf, but still, in some cases, you may hit some problems. So, for example, at some stage at 10.3, I've got a problem to add specific probe that tries to access the structure pointed by some variable. So the query was buried down in that version somewhere. So, and I was not able to access that deep inserted structure, even though I was able to access it with different front end, specifically trace BCC2. So that was kind of a problem, and I tried to find out where somewhere in the code of this function I can get the actual query text. It's available, the only parameter was in another function, like top level one do command. The only parameter was thread. It's one with thread. It's key structure for MySQL and MariaDB, and it's also complex. So there is a query somewhere there, but I was not able to find out. So I moved on and checked what can I access. Actually, perf allows you to access any of the variables that are shown with the vars option, and this is thread with this specific type. But for that specific version of perf and that specific version of MariaDB, I was not able to indirectly move through thread components. But later in the code, they were dereferenced and put into some local variable. So by making this study, I found out that actually I can add probes not only to the beginning of the function, but to actually any step inside the function, almost any step. There is an option called line that shows actually where you can add the probe inside the function. So when I called it for do command, I found out, this is by the way the printout for the debug binaries, I found out each line of the code like an offset from the beginning of the function. That can be traced. And in one of these lines, 157 in that specific case, I found out that we fetch the SQL statement from the thread structure and put it into the command. So as I can add a probe to line 157 and I have a simple variable here, I can try to trace it. And I did. So, sorry, the command was at that moment like kind of statement executed. So I do not need command, but I need a packet that is already there. So I've added this probe, I've recorded, I've processed with perf script and got MySQL statements the same way. While there is nothing new in this specific case, what I've got from this experience is that actually I can add a dynamic user probe to every other code or every other line of code, most lines of the code, in any MySQL function. Now my question is, when you will see every other line of the code instrumented in Performance Schema? Not yet, not even in 8.0. And it's a long way and a lot of work to do. And you will have to change the code statically, compile it, make it bigger, parse it, work on it. It's not easy when instrumentation is every other line of the code. Why I, with dynamic probes and even perf, on any Linux newer than 10 years old, I can do it with just perf anytime. And it was quite useful. It was really a change. So just to give you an idea what else you can do with perf, this time you can do it not only, as I told, I am interested in tools that can be commonly used for MySQL, MariaDB, and kernel itself. So for example, with perf, you can add a probe. It's a trace point for block IO, for example, and check and collect information for all processes with the call stacks for each specific disk IO kernel function, like here. There are more details, surely. What I did also, it has a price, but it's possible to trace every malloc call, every memory allocation with perf. It's just as easy as adding a probe to a dynamic library implementing malloc. If it's default one, then it's in glibc. And printing the address, for example, and the size of allocated block. So we can trace memory leaks, memory allocation this way, but we will add traces only to specific function, only to a period of time we need. It's not like running on the wall grind or whatever memory profilers. It's more lightweight. It can be more lightweight. Again, I documented this. It's also coming from a practical question of one of the developers. Can we find out what is returned by specific function for memory engine records in range? It was needed for resolving a complex optimizer problem, as far as I remember. So there is a request, there is an answer. Small experiment documented in a blog post provided the required information. What's interesting here is that I had to access to the C++ class member function, not just a top-level C function. There are many problems that I hit in the process. We have to still deal with mangled names and everything. And the main problems for me with C++ is virtual member functions. So there may be no address for the function we want to trace when we try to do that. So it's not a universal answer right now. especially when most part of MySQL code is moved towards complex C++. It may not work, but it's worth trying anyway. One of the recent additions to this slide and this talk in general that I'm giving like a third or fourth time this year, basically. Main ideas are the same. Was my attempt to trace pthread mutex log. Again, it was a request from one of MariaDB developers to find out, can we get a stack traces that led us to specific mutex? You can kind of get that from performance schema, but in terms of statements, stages, and waits, not function calls. But you can easily add a dynamic probe and see it yourself. Again, it's all documented. So let's move on. The last but not the least, Perf can be used as a profiler. Not to add dynamic probe, but just to represent the information. This is how it's used. It's still perf record, you just do not add probes. It will be recording performance events. So it's recording the entry and exit to each function itself. And then you can count that. You can keep recording forever until you stop recording by Control-C or by sending a signal. And you can actually use perf top just as I have it. So we can do like that, perf top. And there is nothing fancy, just kernel. But when in another window, I am starting, for example, sysbench, that here works, by the way, with Percona server 5.7, the recent one. We can see how it changes with time. So we can see some MySQL function. We can step in, check what's inside up to assembler level and see where the time spent here in specific function and so on. So it's really cool. And you can just copy paste the top if it's stable enough to see top 10 samples dynamically. So we see that, for example, a client library is used and count for a lot of time. We have performance schema, read-write log, and whatever. Encrypted because I use an encrypted drive. And anytime you can stop this. So it's a real profiler that can be used interactively as well. I will not be concentrated on that. I would rather concentrate on a real-life story that converted me from the performance schema guy that I historically was because I came to MySQL from Oracle background mostly, and there a kind of performance, like a source of inspiration for performance schema is used for probably 30 years already. So it was natural for me to use similar instrumentation and to see the results, and only them, because it was not an open source software. So I was a performance schema guy until I hit one of the real customer issues where I was not able to resolve the problem. Sorry. No matter how long I was collecting the performance data, sizing, and everything, some stages are just not documented. I refer you to the bug reports I've created, actually. So I was not able to resolve the problem. The problem was that simple queries like single line selects by primary key at some stage started to work for many seconds. Under the load with Galera and everything, when some other queries like a good number of updates were executed. So why simple selects can run for so long time? It was not obvious from performance schema, and it was not obvious until I use actually perf. Perf with the -G option showed me a cold stack, and I found out that most of the time, most samples, I actually enter InnoDB function, and it was called from make join statistics in the process and from MySQL select. So the optimizer for such a primitive query still has to decide something. So it has to dive into the index to find out that exactly one value is picked up by the primary key. But for this, it had to enter the InnoDB. In that case, a customer limited InnoDB concurrency, and it was really bad. So most of the time when other like 16 queries were already working updates that had a lot of work to do, unhappy select had to wait in queue. Waiting in queue is not documented separately. It was, I mean, in performance schema, it was shown as statistics, and statistics means nothing. What statistics you need to collect in this case? So Perf showed the problem immediately, and it made me using it at every possible occasion. It doesn't mean that collecting statistics with Perf is problem-free. There are problems. One of them is the amount of data. So if you remember ftrace, and that's why I show you, you have to read the data from some file in that file system and collect it. So you put it into a real file system, into perf data. And the amount of data collected over 16 seconds may be so huge that if we put it onto disk itself for a disk-bound case, we may impact the system quite a lot. So 33 megabytes for 60 seconds is a lot. So overhead of writing by perf record to a user land to the file on the file system may be really serious. How to overcome these problems? It will be a topic for next few slides. eBPF and summarizing the information in kernel context and writing to the user land only what you really need is the answer. Another problem is that call stacks may be really huge and you need to summarize them somehow. You can fold them by different tools similar to what Performance Profiler does, or you can represent them graphically. And there is a great answer again by Brandon Gregg. Mostly great visual representations of these profiles called flame graphs, or another visualization techniques is called heat map. So here in this presentation, I will show you flame graph. Now, what was eBPF? The idea was to process the data in kernel context. So execute as much as possible in kernel and exchange as few information as possible with the user, and still do it in a safe way. So while previous dynamic tracing techniques like system-tap relied on building and adding a kernel module for your probe that also worked in kernel address space and kernel context, when you allow any code to run, you can easily crash and break and everything. So eBPF, initially based on BPF, initially originating from BSD systems, packet filtering. So advanced packet filtering, advanced firewalls requires to remember state. So stateful firewalls are cool, and advanced processing is needed. So this processing had to be done by some software programs. So they created the idea that if we have a lightweight virtual machine and the way to verify the code that we put there so that we make sure it does not crash and it does not loop forever, then we can program this virtual machine and let it do any kind of process. So when it worked successfully for network traffic, next idea was to extend it. That's why the eBPF. Extend the idea and apply to processing all kinds of performance events, trace points, and everything else. So as Brandon Gregg explained, here what we have some user program that is translated to the bytecode of that virtual machine and is sent to the kernel. In kernel, there is a virtual machine that first allows you to verify the code. If the code is not verified, it's not executed. Then, while executing, it provides you access to kernel probes, user probes, static trace points, performance events, performance counters, and everything else. You store them in memory areas, that same kind of ring buffers as we have in performance schema as well, but in kernel context, called maps. And then you have a way to read from the maps. So your software has a way, your program has a way to read from these maps in a sync manner. What was collected there? So how many times functions was called? So there would be a kind of associative array, function name, number of calls, time spent on calls, and whatever else. So it's a map, it's in kernel space. Yes, it takes some memory, but you do not exchange this data, and you do not store in file system all this, everything to post-process it with text processing tools. You can do it efficiently. That's the idea. So you write the eBPF program. Initially, it was written in C, then there was a library created for Python. There are more advanced ideas. And it generates a program for VM, LLVM. That is called the probe. So this program is attached the same way to the specific part of the code as ftrace and perf. Your eBPF program checks the data, checks the content of the probes that are all available to you, and writes something to the map, or to the ftrace file, or to the perf buffer, whatever. And then you can access them in a usual way. So starting from Linux 4.9, we have all the types of events, tracing events that I mentioned. It took some time from 4.1 to 4.9 to add them all in this specific order. I should say that, for example, in 4.4, it's relevant for some Ubuntu. You already have user probes, and I do have it Ubuntu 16.04 that I use on the netbook here for testing. Then real profiling stuff, histograms and whatever were added, trace points, timer profiling. So honestly, you need kernel 5 point something to use all the power of eBPF. You do not need to install anything. You probably rely on some existing front-end BCC, bstate, BPF compiler collection. So this is what BCC stands for. There is a huge collection of them, and if you are not comfortable with writing C code or Python code, there is a less complex front end added recently called bpftrace with a language similar to AWK. So it's like a declarative pattern action, and it obviously shows you that there will be no loops at all, even without verification. So we can consider a few examples of BCC tools in action. One of them, quite important utility, is called tplist, trace probe lists. If there are any static probes added in the code, they can be listed. Thing is, that may be important. While MariaDB does not add trace points by default, static trace points, in MySQL 8.0 they are just removed. So for MySQL 8, tplist and dtrace, formerly inherited dtrace probes no longer exist. For MariaDB it works, or you can compile it so it works. It's not really needed because you can replace them all with dynamic probes actually, so it's not a big deal. But you can see what is there. No point to add another one if static one exists in the code. So to add dynamic user probe, I've used another tool from this collection. It's written in Python and it's called trace. So trace was used in my example again to print an SQL statement. And it's as easy as you know when you know what to trace. So I found out the mangled name of the function I'm interested in, and I was printing third argument. What's interesting, trace understands yet another language for arguments. So argument 1, argument 2, argument 3 is just a positional argument to function call, and there are format modifiers. This is %s means strings, obviously. So I was able to capture the statements as well in a bit different format than perf or ftrace, but still it's 100% dynamic, and it's really easy. So again, there is a blog post with all the details. So I will not show you that much about BCC tools in practice, but there is one slide that rely on one of them as well later. So the last but not the least for today is bpftrace. I will explain a bit later why it's so important recently. Thing is, it's a new AWK style programming language that allows you to create programs for eBPF virtual machine without Python, without C, without low-level stuff. You need recent kernels. I will not show it you running because on my Ubuntu it's not present. So there is a lot of useful examples in tutorials. For example, there is a special syntax for everything. This is how you can access kernel trace points, system calls, for example, or tracing opening files would sound like that. Generic syntax is the following. Pattern, several probes listed via commas, optional filter, so you can apply action only if the probe matches some conditions, and the action, set of statements to execute. It reminds me AWK. So bpftrace is surely simpler than to write Python. Why in the future we will see in a moment. How it looks, well, there is quite a lot of built-in functions, and another interesting built-in prop that allows you to use bpftrace as a poor man's profiler is called profile. So you can execute something at specific time interval at hertz, so many times per second as a profile probe. For example, if the command running equals to MySQL D, I can print user stack in the perf format. There is native format as well. And this is basically what PTPMP uses for GDB. In my blog post, I've used that as well as kernel stack to put an advanced kind of PTPMP that is much more lightweight. And you still get output similar to what you get in the debugger. The key to dynamic tracing is the performance impact that I was speaking about that. This year I made a test on my very old testing box that I assembled myself. I was executing again some sysbench at 12 threads on 4 cores. And what I did, I collected PTPMP profile once a second. I've collected perf profile 99 times per second. So it's much more precise. And I've collected bpftrace profiles 99 times per second. So, and I've measured the performance impact. So performance drops down when you trace. So the result was raw performance versus PTPMP, so huge drop, versus perf, small drop, versus bpftrace, neglectable drop in performance. Why that so? That's because we were collecting already pre-aggregated data. So we used a map, an associative array. For each user stack, we counted how many times it appears. And only when we were done, we were putting the results at the end of bpftrace code into the file. So the file is smaller, like 10 times smaller than what we have seen for 60 seconds collection by perf in another case, and like 2 times smaller than in this case. And it was one of the reasons why it was faster and less impact in performance. So why bpftrace is great? Because it's low, lightweight profiling tool. Another problem, if you remember, is how to deal with all this data. I've shown you one way, and it would be collapsing, aggregating stacks, but you can do more. On top of that, you can visually represent the number of calls per specific function at specific nesting level as a flame graph. You can check all the details. I will just show you the result. For example, I've used yet another BCC tools off CPU time, which is interesting. The idea was to find out where the process goes out of execution. So when it goes off CPU, at which stack traces at which point. And here we see MySQL D, and where what it was basically waiting for. So this off CPU time produced already collapsed stacks. And there is a separate tool by Brendan Gregg, written in Perl, that can work with all kinds of collapsed stacks and create a so-called SVG, scalable vector graphics files, with such profiles that should be opened actually in browser. You can zoom inside, you can look at different parts, you can move over these frames and see function calls, number of calls, time spent if you put it there. It's very convenient way to represent graphically the huge collapsed stacks and still having a way to dig into enough details. So it's great stuff. Now let me try to summarize what we have here. Dynamic tracing on Linux is not problem-free. Let me list some of the problems I noted over the last 4 years of using these approaches. I already stated that you need root access. Well, it's resolved once and forever. There is a problem if you try to debug the program that is already traced. As the code is changed on the fly, the debugger can be fooled down and it may not work well. There is a problem of limiting memory and CPU usage inside kernel context, so you should care to make your probe processing code as lightweight as possible, but that's up to you. It's quite lightweight for basic stuff at least. There is a problem for other tools like bpftrace. It's my own problem, how to point them out to an arbitrary line of the code inside the function, as I did in Perf. I just don't know yet. There are problems to work with C++ because bpftrace needs symbolic information. It's not so easy to use in this regard as Perf. But again, there is a solution. You can provide includes, and there is a solution a bit down on that same slide that is already work in progress for the future. You need to work with recent Linux kernels, but I hope you do so. For all the versions, use Perf, and well, it's just have a bigger impact basically, but it's really flexible. The code should be compiled properly. No omit frame pointer must be used. You must have symbolic information everywhere. In case of MySQL and MariaDB, it may mean debugging for packages must be installed. In some cases, you have to install additional tools, not only root access, but something may be missing on the system. But you can always install Perf and use it without restarting MySQL. And you should remember that ftrace interface that is also quite powerful is already there. So if you know the syntax for the probes you have to add, you do not need to install anything other than root sudo access. In case of eBPF, there are solutions that work for providing the symbolic information once and not having to enforce it installed everywhere. There is so-called BPF type format. Sorry, you can see a link here. That's how it works. And there is also a way to compile the program so that, like BCC tools, that you do not need to recompile them locally. You do not need to install LLVM, Python, and everything. It's called Core, compile once, run everywhere. So this is the future of tracing. And it's actually, Core is what first is applied to bpftrace itself. So currently on modern kernels, bpftrace can just work as is without much additional stuff. And actually, what stops us from using it as DBAs is lack of knowledge. In my case, for example, I also lack some experience with recent eBPF tools in real-life support issues, while Perf and ftrace are already routine procedures for many of our support customers. You may think I'm crazy suggesting such stuff to DBAs, but I'm not alone. Even Oracle DBAs apply these techniques to closed source Oracle RDBMS. They already know some stuff by address and can interpret the code and still get useful results. And with future advanced techniques of eBPF, BTF, and Core specifically, and bpftrace tool, there would be no need to install a lot of stuff. So just study these things, use them, and be happy with the ability to add dynamic probe anytime you need to any part of the code you need, no matter if the developers of MySQL or MariaDB care to provide any other profiling facility. Thank you very much for attention, and thank you, Shivire and MinervaDB, for this opportunity to participate in the conference.